Unusual earthquakes is one of the primary signs of volcanic unrest. As magma makes its way through the crust, it changes the local stress field and may cause earthquakes. Increased earthquake activity may signify the location of new magma flow channels or intrusions, or crustal volume of elevated stress due to persistent accumulation of magma. In areas where the crust is close to failure, the magma flow may bring stress conditions to the failure limit. In other areas, where the crust is sufficiently hot or far away from the failure limit, magma may importantly flow and intrude without any earthquake activity. When earthquakes occur, the associated radiation of energy in the form of seismic waves is used to locate the origin place and time of earthquakes. A seismic station uses a seismometer to detect the ground shaking, now typically in 3 dimensions in the vertical east and north components. The resulting record is called a seismograph, as the example shown in this figure. The type of earthquake shown has relatively high frequency of the shaking and is often referred to as a volcano tectonic earthquake. A network of seismometers is required to measure and locate an earthquake. Seismologists are trained to read and interpret the observed seismic waveforms that can be quite complicated in volcanic regions. Different types of seismic waves are generated that travel through a medium at different speed, typically with velocities of several kilometers per second. P waves or primary waves are due to alternating compression and extension in a media. S waves or secondary waves represent shearing in a medium, and surface waves travel close to the surface of the Earth. Measuring the arrival times of P and S waves on a network or seismometer is an important step in locating earthquakes, but the whole seismic waveforms recorded on a network of seismic stations can also be compared and interpreted. Readings of arrival times together with a model of seismic velocities in the Earth are used to infer the point of origin of an earthquake, referred to as an hypocenter. The surface projection of a hypocenter at the surface, vertically above it, is referred to as an epicenter. Earthquake magnitudes, denoted M, reflect the amplitude of the ground motion recorded, measured on a logarithmic scale. For each whole number increase on a magnitude scale, the ground motion is amplified 10 times. The concept of seismic moment is also used to quantify earthquakes. Seismic moment scales with the amount of slip times the affected surface area of an earthquake. An example of map of seismicity, or more specifically, the distribution of earthquake epicenters, is shown in this figure. The map shows located earthquakes in the Krafla volcanic system in North Iceland in the time period from 1975 to 1984, when a rifting episode occurred. The volcanic systems of Iceland typically consist of a central volcano with a caldera and a transacting fissure swell. The outline of the Krafla caldera is shown and marked with the letters KC on the left panel in this figure. The rifting episode was characterized by magma accumulation under the caldera, interrupted by episodic magma outflow into vertical dikes in the fissure swell north and south of the caldera, contributing to the plate spreading in Iceland. More than 20 diking events occurred during the rifting episode. The 2 panels show epicentral distribution of earthquakes. On the left are earthquake epicenters during all periods when no diking was occurring. Earthquakes focus within the Krafla caldera above a zone of magma accumulation. On the right are earthquake epicenters during the periods of diking. Epicentral maps like this one can show spatial changes in seismic activity and can clearly indicate where magmatic activity is taking place within a volcanic system. Another way to evaluate the seismic activity is to look for temporal changes. As an example, this graph of seismic unrest shows temporal changes in seismicity beneath the Eyjafjallajökull volcano in Iceland, as recorded by the Icelandic Meteorological Office using the National Seismic Network in Iceland. Each graph spans the period September 1, 2009 to April 30, 2010. The topmost panel shows the daily number of earthquakes above magnitude 0.8. The 2 vertical lines show the onset of 2 eruptions: initial basaltic eruption on the flank of the volcano on March 20, 2010, and a later explosive summit eruption that began on April 14th. Note the logarithmic scale for the daily number of earthquakes, going from 1 to 1,000 earthquakes per day. There is a very clear change in seismicity at the beginning of 2010. The time period prior to that had almost no earthquakes, whereas after 1st of January, there were about 1 to 10 earthquakes recorded per day. In the last few weeks, prior to the flank eruption, tens or hundreds of earthquakes occurred per day. This is a clear signature of evolving magma intrusion at depth in the roots of the volcano. The second panel is sometimes referred to as an impulse plot of the earthquake activity. Each earthquake is shown as a vertical line with height equal to the magnitude of the earthquake. There are a number of ways to measure the earthquake magnitude. This shown here is the so-called local magnitude, denoted M subscript L. When many earthquakes occur per day, they will overlap on this kind of a plot, but we can see the size of the largest event. The plot shows that overall the recorded earthquakes are small. The largest are in the magnitude range 3 to 4. This feature of the seismicity, a large number of small earthquakes, is typical for volcanic unrest. The third panel shows a red line that is the cumulative number of earthquakes above magnitude 0, indicated on the left scale. In this case, about 3,000 earthquakes occurred over the time period shown. The blue line is the corresponding cumulative seismic moment in units of Newton meters, shown on the right scale. The slopes of these lines represent the rate of seismic activity. A change in slope signifies a change in conditions at depth in the volcano. The lowermost panel shows the inferred depth of earthquakes, but this is often quite imprecise due to lack of seismic stations directly above the center of seismic activity and uncertainties or errors in the seismic velocity model used. More detailed look at seismicity is often required to evaluate systematic changes in depth of earthquakes, for example, associated with magma moving towards the surface of the Earth. Plots like the one shown here often provide key information for evaluating volcanic unrest.